Okay. All right, so we're back for another week. So we got, what, next week is exam, right, for you guys? Is that what it is? Yeah, it's actually.
Yeah, so that's
Yeah, kind of that same thing there. Hopefully, like I said, I'd always rather do in-person exams for you guys, unless we have to for some other reason. What's that?
Speaking of the exam, I'm gonna try to be hosting a review session with y'all with the other chemistry tutors. So I'm probably gonna be sending out an email and y'all like Canvas page. But when that's gonna be and what it's gonna look like, just so y'all know. I'll probably try to do it like maybe this Thursday, so y'all still have the whole week to study before your exam. But yes, just know to keep your eye out for that.
Cool.
Thank you, Laura.
So keep an eye out there on Canvas and Laura. Who else is tutoring now? Joe is. All right. So keep an eye out for that, and then they'll keep you guys updated. And don't forget, the best way to prepare for a review for an exam is to come in with questions ready, right? Kind of just study a little bit beforehand, go in there, ask Laura your questions, that kind of thing. That will be a lot more productive than just, I'm going to go see what everyone else has to ask. But you guys know yourselves better than I do, right? I mean, I think you guys have been students far longer than I've known you, but just my suggestions on those kind of things, right? So we have that. Let's see. We are going to be finishing up kinetics today. We just got basically one more part to kind of talk through there, the idea of reaction mechanisms. And the reason why I was a little bit late, I'm going to have to burst your guys' bubble about your perception of me. I had two practice problems that we were going to do at the end of the chapter. And I found this is going to be a good practice problem, kind of talk about kinetics. And it's the exact one that's already in my notes. So it is a good example. So I'm really going to help you guys to go through the same thing twice. So I had to go run and grab my book real quick. And so you and I get to work through a problem on the fly here. It'll be great. But don't worry, right? So we've got that. We're hopefully we should get to that. I'll have to see if I can find a good problem for us in the meantime. But anyway, what else did we? So after this, we're going to go into equilibrium, and that's going to be the last chapter. That's going to be on the first exam there. I don't know how far we'll get into it, right? So I'll give you guys a cutoff point, kind of as we get a little bit further through this week here. I always hate to give a lecture on Monday and then surprise, exams on Tuesday, and the stuff's on there. So we'll kind of see how far we get and how far we can reasonably. Let's say, make a cutoff point for that. And it's all right, we're a little bit behind in lecture, but that's not a big deal. Gen Chem 2 is a lot more, let's say, relaxed in some ways than Gen Chem 1 is. There's less chapters to go through, but the chapter's a little bit more complex, and we can always kind of fudge our way around a little bit with which chapters we can cover at the end. Yes, ma'am.
So is the test from your chapter 13 or 12?
Yeah. Yep, so basically from the intermolecular forces moving forward is what it is. Although we didn't really talk too much about chapter 12. Right, in chapter 12, like the materials one there, I forget which one it is in your book. It's like talking about, LCDs and all that kind of stuff. I don't know what questions I asked you guys about LCDs. Like, are LCDs useful, true or false? True. 5 out of 5 points. Okay. What you're looking at on your screen right there, right?
Oh,
Yeah. So anyway,
LEDs?
well, LEDs are behind your LCDs, right? They're the lighting source for it.
What's an LED then?
Liquid crystal display. So anyway, well, like I said, I'll make a call for that later on, and then we'll adjust as we go forward. But I think that's all kind of the let's say the information that I needed to talk with you guys about before we launch back into it. But anyway, so as always, let's start with prayer, and then we'll pick back up there. But Lord, we just thank you for another beautiful day and another opportunity. And Lord, we just, as always, we pray to be good stewards, Lord, of the time that you've given us, of the resources you've given us. And Lord, we just pray that you help us to cast our eyes on the things that you would have us look at, Lord. And we pray that you give us your eyes, Lord, just to see the people around us the way that you do, and that we can share your love and just your joy that you put in us with them, Lord. In whatever way it may be today, Lord, let us be good and faithful servants and just help us to be what it is that you would want us to be to the people around us. Lord, and we know that we're here to spread your kingdom and your message, Lord, and we just pray that you give us the opportunity to do that. And we just ask this in your name. Amen. All right. So, we were finishing up kinetics, and the last thing we wanted to talk about are reaction mechanisms, and I made the point that this becomes more important as you go into organic chemistry. That's really where this stuff is going to come in, and then it's going to pick back up again in biochemistry quite a bit when we talk about enzymes and that kind of stuff. Well, not we, I don't teach that stuff, thankfully. You guys have to deal with it, I don't. So, anyway, when you guys get there, you'll talk about this stuff again, right? But anyway, when we talk about the rate of any process, right, it's what we've been talking about in this chapter. Right? We've discussed how to set up a basic rate equation, and we talked about how to figure out the order of a reaction based off of their data and these kind of things with that, right? And so we got to the point that we were trying to discuss a mechanism. We can break it down into elementary reactions, and elementary reactions are always predictable, and that's some of these questions that you see come out of these conceptual questions that you see come out of the chapter there, where they give you a reaction and say, what's the rate law, right? And so what they're talking about here, if it's unimolecular, it's always first order, and if it's bimolecular, it's always second order, right? And so remember what we're talking about with the order there, right? The order is the sum of the exponents, okay? It's the sum of the exponents. Okay? Complex reactions progress by a series of elementary steps. So basically what we're saying is we can take something complicated and break it down into multiple unimolecular or bimolecular steps. That's all we're saying with that, right? That's all it is. And so that's how you typically see these types of questions kind of written out. We have a complex reaction, and then we start to break down the individual reactions that come out of that, right? So this is the actual rate there, is what it is, but there's no way that we could really know that, I guess, just by looking at it. We'll notice that the exponents don't match the stoichiometry. Of course, that's something we know at this point. Now, that is going to be kind of important to pay attention to as we move into the next chapter, when we get to equilibrium, right? So we'll kind of rescind that statement here. But one of the common mistakes that we get, especially as we add in this equilibrium, is just to make this assumption that in rate laws, the stoichiometry is the coefficient. Don't forget that's not the case, right? Conceptually thinking, right, if we take a look at this reaction, we have two of those iodides, the I minuses, one of the peroxides, and two of the hydronium ions there coming together, okay? So that's a total of 5 molecules. Now if we think about this, and we talked about this last time, for a reaction to happen, the molecules have to come together at the right time, at the right speed, with the right energy, in the right space, at the right angle. All these things have to come together for that reaction to happen, right? And so if we have 5 things, all 5 of those have to come together at the right time, at the right place. That's just not going to happen, right? That's just not going to happen. That's why we can say things like complex reactions proceed in these kind of elementary steps. Statistically speaking, it's much more reasonable for one thing to break apart into 2, or for 2 things to come together at the right angles, yada, 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 that kind of stuff there. You guys catch what I'm saying with this? Right? So that's why we can start to break these things down, right? Remember, when we're talking about reactions, it's all a game of statistics, right? We're dealing with moles of things, right? And even if you think about a fraction of a mole, right, we're still talking about 10% of 10.022 times 10 to the 23rd, right? Is that still a big number? You bet, right? You bet, okay? So a lot of times you can just think of this as, we're using large number theory if you guys have taken statistics yet, right? And that's not a bad way to approach it. All right, so we're gonna kind of work off that last idea there, and that's gonna be kind of how we break apart the mechanism into the individual components here, okay? And so a typical question looks something like this, right? We have that reaction right up there, and they say it proceeds by these kind of elementary steps, got it? And so then they give you a series of steps here, okay? So a couple of things to pay attention to. We'll notice that there are fast and slow labeled steps there. All right, I gotta go close this because like shutting out. Appreciate that. Nobody's allowed to enjoy the sunshine. No, no looking outdoors. I don't know. I remember, because you guys have to sit there and listen to my dumb stories. So I grew up in North Carolina, in kind of the middle of it, in the middle of North Carolina, and snow is not that frequent there. And so I always remember in elementary school, because everyone gets excited for snow days in the South, right? Because as soon as you get an 1/8 inch of snow, it's the worst 1/8 inch of snow ever, right? And everyone has to go run and make French toast because they buy out all the bread and the eggs and the milk at the store, right? Because it's going to be shut down forever. And so I remember, like every time it started to snow over in school, the teachers are like, if you look at the snow, right, it's gonna melt, and you don't get to skip school, right? And so they always like close the blinds. Now the reason why I just happen to remember that is completely irrelevant to anything here. Okay, so back to the point that I was trying to ramble on about earlier there. Anyway, so complex reaction broken down into 3 individual components here, right? Slow, fast, and fast. Now, when we're talking about reaction rates, okay, reaction rates and the individual reactions and the fast versus the slow reactions are like the different lanes on the highway, right? Now, if you guys are like me, I tend to be a very patient person until there's somebody slow in front of me, and then I got places to be, right? Now, this happens worse for me when I'm walking. It drives me nuts. I hate in the hallway, people are just like standing across the hallway, right?
And me.
It's like right in the middle of classes, everyone's trying to get somewhere, and like I gotta talk now, and we've gotta take up space. Get out of the way, right? Get out of the way. Right, anyway, so when we're talking about fast lanes and slow lanes, right? The rate limiting step, right? The rate limiting step, the thing that's going to slow down everything, right, is the thing that's labeled as slow, right? If you're fast, right, then it's not really going to cause a problem. Traffic is moving along nice and smoothly and everything gets going, right? But the slow part of a mechanism is going to be the rate determining step, okay? That's the thing that's going to dominate the overall rate of a reaction, okay?
So it's the pace car.
Yeah, basically, kind of, right? But there's multiple lanes if you want to think about it, right? So we just have to find which one is a slow step is all it is, right? So whenever you hear the term rate limiting, that we're talking about the slow part of a mechanism. It's not the only part of a mechanism, but it's the part that determines the rate, okay? That's all it comes down to. Now, if we break apart the mechanism, we can do it in its individual components, how it happens, right? The peroxide reacts with the iodide to form these 2 components, right? This HOI right there gets immediately consumed in the next step with another iodide to form hydroxide and I2, and then the 2 hydroxides here get consumed and we end up here with our products, right? Now why do we care about this? Well, anything that's formed in between, right? Any species that's formed in between the beginning and the end, right, are what we call intermediates, okay? These are these things that are formed in the middle of the reaction mechanism. They're produced in the mechanism and they're consumed in the mechanism, okay? You guys see what I mean with this? Right, HOI is nowhere in any of my equation here, right? So it's produced and consumed as the mechanism is going on. And the same thing with hydroxide, right? It's produced and consumed as we go on in here, okay? Intermediates. Now, for those of you guys who are paying close attention, you can see that Laura is turning very pale in the corner over there. How important are intermediates in all of organic chemistry? It's everything, right? It's everything. Understanding the intermediate and isolating it and simplifying it and stabilizing and all these kind of things come into this, right? So it's a very, hang on a second, please. Right, so it's a very, very, very important idea to pay attention to. Now, how deep are we going to get into it here? Well, remember, all we're talking about here is the rate of the reaction. But we do have to recognize these things that are produced and consumed in between the reaction there, right? And that's going to be something we have to pay attention to when we get our rate equation out of these complex processes, okay? What's up?
So are you going to give us like a complex equation and ask us to determine what the intermediate steps are and
I could ask you to identify the intermediates. I can't ask you guys to break apart the individual reactions there, right? That's a little bit beyond what I expect at this point. I'm never going to ask you guys, okay, do that. You're like, well, how the hell do I know, right? right? That's what I mean with that, right? So we need more information about that or something along those lines too, right? So, but I would be able to, what I'm pointing out here is things I expect you guys to be able to point out. The fast versus the slow steps, why the slow steps important, what the intermediates are, that kind of thing, okay? You'll notice, and again, this is the point of why I have things crossed out here, right? The sum of my mechanism has to be equal to my overall reaction, right? That's just the way the world works, right? Garbage in, garbage out. What you put in is what you have to get out. And so the individual components in there have to add up to the total, right? But I think you guys already kind of picked up on that, right? So that's just the way chemistry works. Good? All right, so if we take all that and we visualize it, right, this is what we come up with. And you'll notice in each case here, right, we've got a couple of simplified reactions, right? Two things coming together in each case here, right? Now here we have two of two things, right? But those are still individual parts of it there if you want to consider it in that way, right? So seems straightforward, a lot easier than 5 things all coming together at once and magic happening, right? Here are some elementary reactions that do the process or the reaction that we have in mind, right? So that's where we kind of come together with these ideas. Now the last part of this mechanism we'll talk about in about 2 chapters here, quite a bit. All right, so here's kind of the wall of text, thinking about what we've discussed so far there. There's a rate limiting step, it's the slowest step. Here I talk about the supermarket and all these kind of things, right? And here's kind of the things to pay attention to, right? Why can we make this assumption? Well, when we talk about the slow step, right, we're talking about thousands or million times slower. So does it really matter the reaction rate of the fast steps? It doesn't really make that big of a difference, right? That's all it is, okay? That's all we're thinking about. So there is an assumption kind of behind this idea of the fast versus the slow part of a reaction. And we're gonna come back to this idea in the equilibrium part also there, right? In a manner of speaking.
You know, store is even more relatable than a supermarket for a situation like this. Joann's.
You know what that is?
It's a
Oh,
craft
it's like a
store.
craft store?
It's one of these places, like, they never have more than 1 or 2 cashiers working, and so it turns into this thing where there's always like a 30-minute checkout line, and it's the most irritating thing ever.
There's this thing called online shopping.
Yeah, but see, if you really need the exact color of thread to match the fabric you're working with, and you don't know what that color of thread is, and you have to go into the shop with a snatch of your fabric to find the exact color of thread, and then you needed that you can't wait for it to get shipped, and
That sounds rough. There was a question in the back.
Oh, yeah, how do you know which one is the slow step?
It'll tell you, or it'll give you some information about it, right? Yeah, there has to be some indication of it. Good question. Yeah, it's not like, throw a dart and like, that one's a slow one, right? Yeah. Cool. So if we take those ideas and those principles and, kind of start to break this down, right, what does it actually mean? So once we determine the slow step, then I could ask you to write the rate of this reaction, right? And if you write the rate of any reaction, what is it? Right? Rate equals K, the constant, times the concentration of the peroxide times the concentration of iodide to whatever exponents it might be, right? Did we have to calculate what the M and the N are here?
no,
Why not?
because we know it's the first order.
Right? So this goes back to, where was it, right? This goes back to this stage in here, right? The progressive series of elementary steps, what does it mean to be bimolecular? 2 molecules, right? You guys with me on this? If you're bimolecular, what's the order? Second, okay. Right, so is this a bimolecular step? Yeah, and what's the order here? 2, got it? So just kind of something to kind of keep in mind there, right? So a little bit different here at this part. So there's our rates. We could plug in our stuff. We could, if I give you guys concentrations and Ks, you guys could figure all that stuff out, right? Happy days. Everything's nice and easy and just as expected, right? Wouldn't it be nice if it stayed that way? Thank you, Kaylee, that's the appropriate response.
We can always dream of a world that doesn't exist.
Right. Now, the truth of the matter is, it's always gonna be like that, okay? Everything is dependent on the rate limiting step. What's the rate limiting step?
Just a little.
Okay, so all you gotta do whenever I ask you to write the rate of a complex reaction is look for the slow one and say, let me write my rate equation for that. Got it? That's all it really comes down to. Now, here you can see that something a little bit different is gonna happen, okay? So we have this reaction up here, right? We break it down into its individual steps, okay? NO plus Br makes that. And this reacts with another one to make the NOBr right over there, okay? So, what is the NOBr2? We notice it's produced and then immediately consumed in the next step. Got it? So that means what? It is unintermediate, right? Got it? Then this reacts with some more NO, which we started out with, right? That's our initial stuff up there. And it makes our product that we have in our reaction like this, right? So you guys see how the NOBr gets used and consumed in the subsequent steps there. Got it? So if I ask you guys to write the rate for this, and that's what you guys would come up with, right? Now pay close attention. We say that rate is equal to K2, right?
Is that because it's the second step?
So there is a, right, this is the second step and there's a rate for that one, right? That's all it comes down to, okay? And you'll often see this labeled in the book as K1, K2, K3. We might even see K minus 1, right? And let me explain to you what that is. So take a look up here at the fast step. We'll notice we've got these arrows pointing back and forth, right? We're saying that there's a forward reaction and a backwards reaction, okay? The forward has a rate and the backward has a rate, right? They'll have individual rates, okay? And so oftentimes what's kind of missing on here, or what you guys will see, is that you'll see something labeled as K1 and K minus 1, okay? The forward rate and the reverse of minus 1. That's all that's referring to. Got it? And then the second step there will have K2. If there was a third step, it would have K3. If K2 was reversible, you'd have K2 and K minus 2, right? That's all it is. Those K's are just constant for the reaction in the direction the arrow is pointing. Do you guys treat those any differently? No, right? So you guys with me on this then, right? So that's where the rate equals K2 times those two concentrations come from, right? But because of what we were talking about earlier, right, there's a problem. We can't really isolate or measure most intermediates, right? They exist in instantaneous, right? And so if you think about it, one thing that we've made an assumption with all along is, how in the world do I measure the concentrations, right? Because everything we've been dealing with is concentration. Well, how do you measure a concentration? Huh?
Light.
Yeah, you could do spectroscopy, right? So there are a couple different spectroscopic techniques. I think you guys will be doing this at some point in the lab. What were you guys making in the lab? I saw a bunch of like black powder and stuff around there. What are you guys doing? Huh? Tungsten oxide? What in the world do you do? What are you guys doing with it?
You're doing intercalation.
Conductivity.
Conductivity?
Yeah,
That's a new,
first we basically transformed tungsten oxide, like mixed it with zinc and
we intercalate like hydrogen into the tungsten oxide and
Oh,
compare the conductivity.
it sounds cool. What are you guys, like, what are you guys gonna be calculating and learning from?
amperage and
Resistance.
Oh, so, stuff that we learned about 6 chapters. Okay, cool. All right, yeah, we'll get there. It sounds super fascinating. Like intercalation is actually super duper important.
Dr. Ton wrote this lab himself apparently.
Yeah, it's amazing.
So the good news is he's open to criticisms about it.
Well, let me make this statement. So before I came down here, my job was running all the teaching labs, and getting a new experiment into the lineup is always a challenge, right? I wrote multiple lab manuals, and every edition always had problems with it, right? You know, sometimes you just gotta try something and see how it goes, and then you
It
adjust
worked
as
pretty
you go
well
forward,
that
right?
last week.
And that's what I would say with you guys in all honesty is just, you know, every professor, man, I feel this looks like story day with Dr. H. Right? Right? Every professor is always interested in useful, criticism, I would say, right? If you come to me and tell me I suck, like, okay, thanks, right, you know, can you leave my office now? If you come in and say, well, hey, it'd be really useful if you did this, or if we tried this, or I'd like to know more about this, and that's much more useful to us, right? So, it sounds really fun. Intercalation is actually really, really important in a lot of different fields. So hopefully something good comes out of that. Besides, like I said, you guys will be learning about this stuff in a couple of chapters. That means when we get to the electrochemistry chapter, you guys already know it all. Why are you guys all laughing?
Because like we
Gotta know.
do the stuff in lab, that doesn't mean we understand what we're doing.
You guys are just hoping just to pray to get through it all, right?
Pretty much.
Dear Lord, I just need an A because everything gets easier after Gen Chem, right? All right, so here we are, right? So there is our fast reversible reaction, right? This will be important when we have the K and the K minus one, right? And our slow step there, all these kind of things. I think where I was getting to with this is we can't really measure most intermediates, so we can't derive a rate expression based off of something we can't measure, right? If we can't measure something, then my value of the NOBR2 there is what? Unknown. How can I calculate anything? I can't, right? So what we're going to have to do is take the thing that we can't calculate and express it in things that we can calculate. Got it? So all we're doing is what you guys have seen or what you guys have done before in algebra, where you have two functions, right, with two variables, and you just have to express one variable based off of the other one then, right? That's all we're doing here. Okay, so how do we do this? Well, we take our first part of our reaction there, right? And we can write our forward and backward rates, right? You guys with me on this? Now, we're going to talk about why we can do this in a little bit, but just for, well, I guess I can do it now also, right? Equilibrium is just defined as the forward and the reverse reaction rates are equal, right? That's all it is. So that's a just mathematical expression of what equilibrium is. Got it? Is there anything different with the expression of rate here? Nope. K times the concentration, right? K times the concentration. Got it? So nothing different there. But if you notice, now I have an equation that has my intermediate in there. Got it? And this intermediate can be expressed by things that we can measure, aka our starting values. Right? Can we control how much NO we put into this reaction? Yes. Can we control how much Br2 we put in this reaction?
Yes.
Absolutely. You guys get what I mean with this? If it's part of our starting material, right, the stuff on the left side over there, then we can control that, we can measure that, or that's the assumption that we make, right? We can measure and control that. And it's true in this case. So I rearrange, right? All I do is divide by K minus 1 here, right? And get this expression for my concentration of my intermediate. Got it? And I think you guys know where we're going next with this. So we take the law we had earlier, right? We bring in our new expression for the concentration, and we just do a little bit of simplification. All our K's lumped together into another K prime, which is just the sum, or not the sum, I should be careful here, just the complete expression of all the different rates, the rate constants, into that one K prime there, okay? Why is this useful? Well now, right, everything is a function of our starting material, right? The stuff that we can actually measure. No intermediates are in there, right? That's all it is. Got it? So what's the tricky part of this stuff?
Everything?
No. What's the tricky part of these types of problems? Finding what's the slow step, right? Identifying your intermediate and getting an equation where if your intermediate is part of your rate, you can express that, right, as a function of your starting concentration or something you can measure. Does that make sense? That's all we did, right? Alright, so if we take all that stuff together, alright, this is kind of everything, and we talked about the last couple of slides there for the last couple of minutes. But I think you guys, I don't think I need to read this out for you guys, but I'll give you a second to kind of look through it and copy down if you need to. But, there's just kind of what we're dealing with mechanisms and that sort of thing. And I think, is that the end of what we have? Yeah, we could say that's the end of it. Cool. I think there's a couple more slides. I've worked through another problem in there, but it's all the same idea. So I'll let you guys look through that. Okay, so that's kind of the end of the kinetics chapter there. Yeah, what's up?
Real quick on the last slide.
Yep.
The final equation was rate equals K prime.
Yep.
What is the prime?
It's the K, what is it, K1, K2 over K minus 1, right? So it's this, right? Just take
Right.
this into a new expression of K, that's all it is.
Okay, nothing canceled out there though, it's all.
No, right there, we don't know what those Ks are, right? And they're gonna be, they're gonna be different for the different rates.
So then how do we find K prime?
I'd have to give you some information about it. Right, here's our expression, we've got rate, K, that and that, I'd have to give you information about something in there, right? Or I'd have to give you individual information about the parts of K prime. There's only there's, again, as with everything in Gen Chem, I have to, if there's 5 parts of your equation, I have to give you information about 4 of them.
Right.
There's nothing that you guys are expected to just magically know, right, with no prior reason. Good?
I have a question on the slide after this one.
Yep.
It says if a rate law matches stoichiometry, it could be elementary or complex. How
Yeah.
do we make that distinction?
We don't know, we'd have to have some other information about it, is what it is.
Will that information?
Well, remember what we're saying with an elementary reaction, right? This is what we're talking about in here, right? If it's elementary, it has to obey these laws. The complex ones don't necessarily have to, but they can, right? So I'd have to give you some information about that, is what it is. So if I tell you this is an elementary reaction, then you know that, right?
Okay. Thank you.
Mm-hmm. Cool, all right. So, let's switch over here. Some blank paper. And cool. So let's suppose we have a reaction. Good old generic A plus B goes to C, right? And we have some information here about some experiments that we ran. Cool. So why don't you guys tell me what the rate law is? So you guys can tell me what the rate law is. first I would say write the rate law for this here. Right? That's kind of. Any generic rate law code can be written the same way. What does generic rate law look like? Rate is equal to what? Rate is equal to K times what? Any rate is equal to K times the concentration of A to the M, B to the N, C to the Q, blah, 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 right? Now your job is to figure out what the M and the N are, using that stuff there. Right? So what's that equal to then? So anything to the 0 is equal to 1, right? Yeah.
Hey Doc, I think I've done something wrong. Am I on the right track
Yeah,
here?
that's good.
Cause this would come out to n equals 1/2.
No.
Yeah,
Nope.
I'm trying to figure out what I did wrong.
The square root of 2 would not be equal to 1, right?
Oh, that's not.
Remember guys, anything to the 0 is equal to 1, right? So 2 to the 0, 5,000 to the 0. So remember when you're starting this out, always be in your best interest to write out the generic rate equation, right, for the reaction, right? No matter what, all the complex things that we talk about, right, if we were just looking at a reaction, rate is equal to K, the concentration, raised to some power, times the concentration, raised to some power, times the concentration, raised to some power, blah, 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 right? So if we had 15 parts of it there, we could still go back and do all that kind of stuff. Although obviously, we'd have to go back and do a little simplification if that was the case, right? But here we go. So, do we have information about the concentrations of A and B? Yep. Do we have concentrations about rate? Yep. So what do we need to figure out? M and N. Got it? Remember, if you see a setup like this, what you gotta do is compare your rates, right, at two different, let me change colors. Compare your rates at two different reactions. So a rate of 2, right, over the rate of 1. What happens if I compare the rates of 2 versus 1? I keep my A constant and I change my B, right? That's all it is. So if I do this, just start to plug in some numbers. A rate of 2 is 4 times 10 to the minus 5. Rate of 1 is 4 times 10 to the minus 5 equal to K. K, that was a bad line. Concentration of A is 0.1 to the M, 0.2 to the N, here's 0.1, and 0.1. Just make that look nice and pretty good. Good? Why is this useful? What can we do? The k's cancel, right? 0.1 to the n, 0.1 to the m cancels, right? And so we're just left with an expression of n, right? So if we simplify this, let's start to cross things out, right? That divided by that is 1, right? This cancels out with that, that's equal to 1, that's equal to 1, right? So here we have then 2 to the n, right? If we finish that off. What does it mean if n is equal to 0? What does it mean if n is equal to 0? In our overall rate? Yeah.
That concentration will be 1.
Yeah, right? Well, hang on. Not the concentration is equal to 1. The impact, right? The impact on the overall rate is nothing, right? But you guys already knew that. What does the rate tell us here, right? Take a look at what I did in experiments 1 and 2. I doubled the concentration of B, and what happened to the rate? Nothing. Got it? So without even doing the math, you guys can kind of visualize this and say, oh, well, the concentration of B has 0 impact on the overall rate. Do you guys catch what I mean with this? So when you look at this through the book, or if you even do some videos online, or like some people just say, oh, just do this visually. Well, you can do it visually, right? You can do it visually. If you're like me, you've got dum-dum days, right? You guys have those sometimes?
I have dum-dum months.
You guys know what happens on those days? You look at something and you say, oh, well, the concentration doubles and my rate stays the same, so my n is equal to 1, right? But that would get you to the wrong answer. Okay, so be careful of that, right? Be careful when you do this stuff visually. What's the way to always get this right? Do the math. Got it?
Wait, wouldn't n be equal to 0?
Yeah.
Okay.
Yeah. N is equal to 0. But I'm saying if you're doing it wrong visually, then you say, oh, there's no change, n is equal to 1 type thing, right? That's a common mistake to happen. But that's not the case, right? N is equal to 0. Cool. So how would we solve for m?
Same way.
The exact same way, right? Except we would do what? We would pick
1.
3 versus 1, right? Cool? And what did you guys get for m then? Can you guys see that visually? What happens when I double, right? What happens when I double my concentration of A with my rate? It goes up by what?
4.
4, right? What's my relationship between 2 and 4? Well, I square it. Got it? You guys with me on this? So, if I do my math, then I would get m equals 2. And so if I come back and plug everything in, right, rate is equal to K, concentration of A, squared, right? Yes?
So you said you would do 3 and 1 for finding n, because, is that because in 3 and 1, that's what A changes?
The A changes and the B stays constant. Remember, I need to keep constant the thing that, I need to keep one of these things constant to figure out what the m is, right? So I want anything with that n to cancel out. Good? How are any of these problems solved? The exact same way. Got it? There's no trick here. What is the trick though? Just making sure you pick the right reactions and follow through with your math. Got it? That's all there is. Wonderful. We have a little bit of time then to introduce the idea of equilibrium. And maybe on Wednesday or Thursday or sometime when we have a good break point here, then we'll come back and work a couple more problems out of here. But take a look. What I will say about rate is that this was always one of these things that was scary to me when I was going through Gen Chem 2, right? It was difficult for me to conceptualize it, kind of what's going on, right? The idea of rates and all these kind of things. But I think I've shared with you my secret before, right? What's Dr. H's secret to success?
Keep units.
That's one very important one. You just got to do it, right? You got to start working some of these practice problems. And I know, I can already hear it. Dr. H, you don't understand. I'm really busy. Or, I don't really like this stuff. Or, I feel so lost and I don't understand a darn thing. Right? I probably hit 90% of you guys with one of those 3 statements in here. Okay? And what I will tell you again is that all those problems can be fixed. All of them. Okay? We can help you understand a little bit more what's going on. Okay? You can start to feel a little bit more confident about what you understand. Right? But when does that problem need to be fixed?
Before the exam.
Today. Got it? Because what happens on Wednesday of next week? I didn't get everything right. Right? You guys get what I mean with this? Like I said, that's all it is. Just come see one of us. You don't want to come talk to me? Fine. Go talk with Laura. You don't want to go talk to Laura? Go talk with Joe. You don't want to go talk to any of us? Go talk with Dr. Tom or Dr. Freeze. Right? All of us are here to help you guys out. Okay? But you got to get it done. You got to work some problems. Where do you start with the problems? In the textbook, start with the ones that are nice and worked out in the chapter itself. Right? It walks you through it step by step. And then immediately after it walks you through step by step, what does it give you next? The exact same problem, then guess how you do it? The exact same way. Got it? Right? So start with that. Good? Alright, let's get into something a little bit more. Oh, crud. I didn't even bring my lecture slides. Alright, you know what? So that's just a great start to a Monday. So, you know what? Why don't you guys go have the rest? That was a dumb move. Speaking of that. Alright, so you guys enjoy a little bit of extra free time here, and we'll pick up equilibrium next time. Alright. So lesson learned from me. Double check my slides.
Honestly, Doc, that's super relatable right
Yeah,
now.
well.